So there is an ice pick which is balanced on its point. Say, making an exaggerated drawing here. It is resting on a rough, strong surface, and now we need to find that using the Heisenberg uncertainty principle, by which we mean the position momentum uncertainty, and using this we need to see that for how long this can stay on its point, sharp point, and what is the minimum time for which it will stay using the Heisenberg uncertainty principle. It will stay on its balanced point. So let's say the length is L. I'm just going to make a single line to demonstrate this toothpick. So let's say it starts with length L after a certain point. So it makes an angle theta, and now it is here. So let's say from the center of mass point there is a force downwards, which is mg, and this is mg sine theta. Because this is theta, so this will also be theta. Okay, fair enough. Now, since this is an angular movement, so there must be some torque responsible for this. So we can write a general formula for torque which relates the moment of inertia and the angular acceleration, or to write more general form in terms of theta, angular displacement, this will be theta double dot. We can write moment of inertia as mass times length square, so that would give us torque is equals to L square theta double dot. Let's say this is equation 1. Also, torque is equals to distance times the force. So here the distance is L and the force is mg sine theta. So torque is basically mgl sine theta. Since we are taking a very small angular displacement here, I can approximate sine theta with a theta, and it will be mg theta. Right? Okay. So this is my equation 2. Both are torques and they must be equal. So using 1 and 2, you can write L square theta double dot. Oh, sorry, there is an L here. So that would give us, there is L There is G dot. Where I have defined the length is equals to this, the frequency, angular frequency. This is equation 3. The solutions of this can be written as times exponential omega t is b times exponential times t. Okay, fine. Okay, so as time goes up, this part also, this part decreases. But we know that as time goes up, the angular displacement will increase and not decrease. So we say that p is equals to 0, right? Okay. So the angular displacement is a times exponential omega t. Okay, fine. Now we need to find the value of a. How are we going to do that? Okay, so we are going to assume this distance is x0. This is theta, this is L, this is L, this is L. So theta is equals to x0 by L, to give us 0 as theta times L. Also, we know that this theta is a times e power omega t L. Now we make the approximation that theta is, the time is very small, so this term will be almost 1. Okay, so x0 is almost a times L. Okay, fine. Similarly, we find the momentum, which is mass times velocity, which is called theta dot. Dot L, so it will be actually rho is equals to m, the corresponding p will be mx dot. This will be mx dot. So give me theta dot L. Okay. What is theta dot? For theta, we found the general solution as a exponential omega t. That will give us a omega power omega t. And again, we make approximation for very small time. That would give us m a omega L. This is the momentum part. Now from the Heisenberg uncertainty principle, this is for our case, this is the H bar point. Thus, L if we want to take the minimum bar, we can write this as equality so that will make A as h bar over 2 m omega L square to the power 1 by 2. So that is what we were interested in. So now the theta is h bar over 2 m omega L square power 1 by 2, and e power omega t will be just 1. I will not take it 1 right now, let's keep it power omega t. Okay. Right, so this is how we can move forward. Since the theta must be in degrees, we multiply by pi by 180, and this 1 by 2 will come in the front because of the logarithm, and there is omega t. So if we proceed further and keep the time the left hand side and divide the entire term by omega, we get this result. And if now we assume that, let's say, the theta very small is 1 degree and the mass value is, let's say, 1 gram, and if we plug in all these values here, what should we get? So when you plug in all these numbers, you will find that it's coming out roughly be around this. Which is roughly 1 second. Okay, so from Heisenberg's the toothpick can stay for 1 second without falling. And the length that I used is the length, 1 centimeter, or means 2 meters.